I'd love for you to just introduce yourself to folks and give a little potted history of who you are. I'm sure you've done this 1,000 times. It's been a busy week.
Yeah. Well, first, Matt, thanks for having me on. This will be fun. I'm Anders Hejlsberg. I'm a technical fellow at Microsoft, and I work these days as the lead architect of the TypeScript open source project. Before that, I worked for a decade on C#, and before that, I worked for a while at Borland on products like Delphi and Turbo Pascal. So, been doing software development tools, programming languages for over 40 years now. It's been a long haul.
A bonkers career. Yeah, absolutely incredible. Yeah. And we are here today for a specific reason, which is that TypeScript has announced an incredibly exciting thing. I'm sure that if you're on this stream, you know the announcement already, which is TypeScript is porting to Go and spending, I think, the next few months or most of this current year to rewrite the code base. And I mean, it's been a massive reaction, right? Like you guys must be absolutely buzzing about it. How are you all feeling about the reaction so far?
I think the team is super excited. We've been excited for a while because we've seen this 10x, that now everyone else has seen too, and that is just a shot in the arm. Like every time you write a piece of TypeScript, it's like, oh my god, that was fast. So the team is just super excited to be public. We're super excited about the positive reaction from the community, and it's fun to already see people putting up pull requests and creating a playground that uses WASM and does. I mean, it's like the energy is out there, and it's just that's what keeps us going. Is just like the appreciation that the community has for the work that we do.
Yeah, that's cool. I watched another of your videos that you did, and it kind of leaked internally. Is that right? And people at Microsoft were talking about it and asking for it and things. Is that right?
I wouldn't say it leaked. I mean, it's internal. So we didn't run around beating the drum too much, but we didn't try to keep it a secret in particular either. We asked that people be discreet about divulging it. But other than that,
wonderful. I mean. I also saw that Daniel was saying, Daniel, the project manager of TypeScript, he was saying that you could potentially see a CLI released in a few months, right? In sort of springtime, let's say. I mean, sorry, Karen.
Yeah, I mean, we're working towards parity with the old compiler, and probably the first parity milestone that we'll reach is the command line compiler. We're not there yet, but we're definitely getting closer. Currently, the type checker doesn't support JSX and doesn't support JSDoc. And because we wanted to take this opportunity to do a bit of re-architecting, the JSDoc in particular was kind of not done the way that now that we have the experience with it, we know the right way to do it or a better way to do it, and so that's what we're doing. I don't expect that will take all that long, a few more months. So this summer we should have something, I would imagine, for the command line compiler, and in a sense, for some customers, we already have something now. I mean, if all you do is use .ts files. There's no TSX in your no JS being analyzed by the type checker. Well, then we're pretty darn close. And as you saw in my demo and announcements, we already compile like very large projects like VS Code with no errors at all, and we do it 10 times faster. So and of course, if you also introduce an error in that project, we will catch it. I mean, it's easy enough to compile with no errors at all, right?
Right. So, we compile VS Code at 10 times speed, but it's all a false positive.
Our existence proof is kind of like that nothing happened, right? I mean,
nice. Yeah. Interesting. So, like the path then to getting full parity, you've got a lot to do, right? You've got the compiler. You've got you need to do project references and all the build stuff and all that kind of thing. The IDE integration, you've talked about that you were changing the LSP as well. I guess my question here is like, what unknown unknowns are there still in the future? You know, like there's a TV program in the UK called Grand Designs where they're building a house and everything falls flat and like nothing goes right and it delays and delays and delays. Like what kind of things do you see in the future?
I think a couple of things. We're still exploring how to build a consumable API that can be consumed from any other programming language, because now the type checker, previously, our API, in a sense, was the code itself, right? Because it's JavaScript, and in JavaScript you can call anything you want, and people did. So all of the internal implementation details of the compiler were effectively revealed and available for anyone to party on, and lots of people partied on it. And now we go from that to it's all sitting in an exe. And by default, there's nothing to talk to unless we put in something to talk to. Now, we're definitely putting in LSP, the language server protocol, such that IDEs can talk to the language service, and which in turn is simply a veneer around a compiler, right? And talk to the semantic oracle that sits in the box and can answer the hard questions of, what is the type of this and what are the members of this and so forth. Where is it referenced? Now I lost my train of thought where I was going with this.
You've got the LSP. That's what you're aiming at.
Yes. So, but it's still an out of proc or inter-process communication of that has to happen there, right? An IPC.
Yeah. Where it wasn't before, right?
Where it wasn't before. And that means, the cost metrics are different. It's more costly to make an inter-process call than it is to just make an in-process call. And so we have to, A, think about how do we get a performant API, and B, how do we get an API that is factored appropriately such that, we reveal the details we want to reveal and keep it versionable downstream, right? So that stuff we're exploring right now. How to best do that. But we know for sure that our API is going to look different than the current API, because the current API is basically the entire compiler.
I guess the thinking there is that you're going to maintain two separate versions of TypeScript almost at once, right? You'll have TypeScript 6, which is
correct. Yeah, there's the 6x lineage, i.e. the old compiler, which we will continue to maintain until we have reached what we will deem a full parity with, but full in quotes, right? Because like I said, like certain things, it's simply not possible to be. I mean, the only way you can be exactly like the old compiler is by being the old compiler. And we know that we're not going to be that, right? But we're actively talking to teams in the ecosystem about how their tools can best target this. And I think we'll get there, but that's definitely an area of exploration still. And then I think there's also a lot of thinking going on about how to structure the language service. We know that a lot of the things that language services do now are better done if there's some involvement of AI. In like say refactorings and what have you. Instead of calling it my function whenever you refactor, how about we have AI dream up a better name for it, right? And so some of these these features might land in a more Copilot-y part of the service, than in the base language service, right? But we're definitely committed to implementing the basic LSP functionality. Absolutely.
Yeah.
So, yeah.
Okay, so the unknown unknowns are kind of the shape of the public API and how that interfaces with the community stuff. And then, how this relates to AI, I suppose, which of course is an open question to all of us. Interesting. what I did before this interview is I went around a couple of people and I asked them questions that they would like to ask you. And there was something in the community feedback that sort of came out that I thought was interesting, and I wanted to get your thoughts on it, which was that the way that Go integrates with WASM has a little bit of, has some issues, right? And when you're running TypeScript on, or when you're running the TypeScript compiler on the web, you need to somehow interface with a TypeScript compiler. And if it's written in Go in WASM, I'm wondering what kind of performance issues there might be there. Evan Yu, the creator of Vue, posted about this, and it seems pretty credible. And that was a question that he wanted to ask.
Yes.
So I'm sort of speaking as Evan there. I'd love to get your thoughts on that.
Sure. We definitely experimented with once we got far enough in this project with our initial prototype that we could get data on, like that indicated we could be 10x. We of course were very curious about, well, what does it mean for WASM as a target? Because we knew that we're going to have a playground. You're going to need to run this compiler in a browser, and so we built a WASM target. And experimented with that, and it looks to us like we basically give up the gains when we're running in WASM, which means we run about the same speed as the old compiler, which was certainly acceptable to everybody else. Now, it'd be nice to run faster than that. It'd be nice to get all of the 10x. There is some work that would need to be done in Go's targeting of WASM, and likely in WASM itself also. I mean, best I understand it, there are a couple of features that, well, there's one feature in particular that Go needs in order to truly do concurrency well, and that's the ability to do lightweight stack switching, or green threads, if you will, where Go routines basically switch the stack when you're switching execution context. And in WASM, the stack is heavily abstracted, and you can't really do that. So they're forced to emulate the stack, and that's costly.
I see.
That in turn, as I understand it, and I'm not 100% sure here, but there's this new feature, WASM GC, but again, until WASM GC also integrates with stack switching, it isn't really possible for Go to use WASM GC, which means they have to carry their own garbage collector into the WASM box and basically, start from first principles, right? Now, I think over time, these things will get better. And I think they are good enough at this point, but yes, I mean, nothing is perfect, right? Everything is a compromise here. But when you sum it all up, I think the other benefits we get from moving to Go, as opposed to some other, like in this particular case, well, Rust, some would argue, might be a better target for WASM, which is probably true at this point in time. But then, as has been discussed, extensively, we would have had a whole bunch of other problems that we didn't bargain for, like implementing an entirely new memory management scheme and breaking all of our cyclic data structures into God knows what, because Rust doesn't really have an answer to that problem. And that's an even bigger problem. So, you can't win them all, but I think we have an acceptable story for WASM, and I'm fairly convinced that it's going to get better.
Yeah, I can tell that the Rust versus Go stuff is just in your muscle memory at this point. I mean, I think I'm really keen to keep this conversation focused on TypeScript only. And by the way, folks, if you're interested in why TypeScript chose Go, I've linked to an extremely good GitHub discussion from Ryan Kavanagh, who has explained the entire thing beautifully. I think actually you guys handled that really, really well and anticipating that. So I don't want to rehash old ground. Okay, so the idea is that the WASM is essentially you're aiming for not a degradation, really, and it's kind of the problems are downstream of you, it sounds like. Yeah. Basically, that's the short story. Yeah. Interesting. So, okay, from other conversations I've heard with you, it sounds like the gains that you're saying that 3.5 times, let's say, is from the switching to a native language, so moving away from JavaScript, JIT, all that stuff, and then 3.5 is from parallelization, right? So parallelization is kind of part of the big gain here, and concurrency, and I'm wondering, you mentioned that the amount of cores that you're throwing at this is kind of like limited to 4 at the moment. You can't necessarily parallelize across all of the cores in your, your setup. What is that?
Well, it depends on which phase of compilation you're talking about. And so let me first describe, they're I'd say we have about 4, you could think of it as 4 or 5. Well, I'd say let's call it 4 phases of compilation that we have. There's parse, which is when we take source code and turn it in and build an AST, an abstract syntax tree data structure in memory to allow quick navigation and understanding of what's in that source file. Then there's binding, which basically resolves names, or sorry, it doesn't resolve them, but it finds it finds declarations of names and builds simple tables in their scopes, such that in a further phase called checking, we can now use those simple tables to look up names and understand what they resolve to, and then that in turn allows us to resolve their types and their names and so forth and so forth, and that in turn allows us to then check that the types are compatible. So that's the third phase, the check phase. And then finally, and you may or may not use this phase, there's the emit phase, where we turn your TypeScript into JavaScript, possibly down-leveled, transpiled, right? 3 out of those 4 phases are what I call embarrassingly parallelizable, meaning they are problems where you are operating in isolation on a single source file at a time, and you can simply scale by assigning different source files to different cores and have them do the work. And so that's what we do for parsing, and that's what we do for binding. We literally create a Go routine for every source file, and off to the races we go, and we let the Go scheduler handle just pushing through as much work as possible. And that works beautifully and scales.
I imagine other native tools like SWC and ESBuild, they can do similar things, right? Because they're not checking types. That
is the whole sort of point of Go support of Go routines, right? And so we take advantage of that. And we do indeed see linear scaling. Now, modulo I/O bandwidth. I mean, at some point, if you have a whole lot of cores, you may not have an I/O system that can keep the course busy. Right, and so we do see some contention there, because often they all arrive at the same time. They all want to read a file right now on top of each other, right? And so, but by and large, it scales linearly. Now, and that's because these are problems where you can just isolate the operation for each single source file and then just divvy it out. Now, checking is not exactly like that, because checking is all about analyzing the whole program view and checking that everything is correct. Now, a check basically consists of take each source file in the program, do a full AST walk, and then find all the places in the AST where there's something to check, and check it. For example, and that, of course, like if you have an expression x plus 1, well, the check would consist of resolve the type of x, which in turn means go look at in the simple table where was x declared. Once you have its declaration, does it have a type annotation? If so, resolve that. If not, does it have an initializer? If so, figure that out recursively, and so forth, right? Until you have a type. And now check that type is number, since you're adding 1 to it, and so on, right? Now, this resolution process, mind you, though, is, even though the check proceeds locally by walking the AST and checking each individual source element, this resolution process will actually often jump all over the place, right? Because let's say X was declared as X colon foo, and but foo is over in this module. It was imported from up here that references that module over there. And now all of a sudden you're doing resolution work over in this other source file over here. So you're jumping all over the place, but you're being driven by a linear process. But then you're sort of fanning out and getting stuff from everywhere, right? Now, one way you might envision parallelizing this is to say that, okay, well, we're going to build all of these, we're going to materialize all of these types, and sort of relate to each source element or declaration or identifier, what is the type of this thing? Let's change our compiler such that it is threat safe. And then let's just set all N cores off to the races, partying on the same mutable data structures, and let's protect them all by mutexes and whatever. And oh my, that would be a huge undertaking, and could also lead to a lot of contention. That this is not how we approach the problem. This is how you would, in a sense, try to make it parallel in the classical sense, right? But instead, what we do is we sort of take a shortcut, and we say, okay, we know that once we build our abstract syntax trees, and once we bind them, we have this data structure, and by design, we have a data structure for each source file that allows us to navigate and look up names and whatever. Once we go through the parse and bind phase, we consider that data structure immutable. It just sits there in memory. We never change it again. And that means that if you have multiple projects open in a language service, you only have to build this data structure once per source file, even if the source file is a member of multiple programs or projects that you have open, right? And we were already designed that way. Now we can leverage that architecture by, in the type checking phase, instead of having one serial process that type checks each of your source files, we can take your program and then divvy it up into chunks. Like, say we divvy it up into quarters. Yeah. We say, here's a quarter of the source file, another quarter, another quarter, another quarter. Then we create 4 type checkers. We give them each the full program view. So we tell them, here's the program you're checking, but you're only going to check this quarter of the files. And then we just set them off to work. And now it's as if you have 4 checkers that don't know that each other are there. They don't know about the existence of the other checkers at all. The only thing they share is a big immutable data structure called the program, right? And then they just go off and they serially check each of the source file assigns to them, which means they branch out and resolve types over here. So there's some duplication of work for things that are shared, if you will, like the lib.d.ts types and whatever, right? And so we
globally available types and things.
Exactly. So we duplicate some work, but it turns out that it's not that much work. Most of the check work is very local, like grammar checks, completely local, checks of local variables. Yeah, well, they're obviously local because no one else sees them, right? And so most of the work is local. So it scales very nicely, but it does consume more memory because there's some duplication of types and information that we build in each checker, that isn't shared. But the benefit is that they can all run at full clip and no synchronization is needed whatsoever in between them, right? And so they just like party on at full throttle. And then at the end, they're left with a list of error messages that they each would like to present, right? And then we just go in and harvest all the error messages from each of them, remove all the dupes because often there are duplicates, and then now we're done, right? And this scales quite nicely, but it comes with a couple of caveats, like I said. One is it consumes more memory. And let's say you have 32 cores, right? Well, now you're going to get a lot of things duplicated 32 times. And so what's the trade-off there? If you have a lot of IO contention anyway, and so we're still learning about what the best way to sort of divvy it up is. What's the best algorithm for it? We also know that technically there are parts of the compilation process that depend on order. And what I mean by that is like who gets checked before who, or who gets what type gets resolved before what type. And if we want to elaborate on an error message, we only elaborate once, because let's not give you the same like error pyramid umpteen times. Let's give you the pyramid once, and then if we've already given you the pyramid, then let's just tell you the top level thing. Foo is not assignable to bar, because we already told you why. Let's not just flood the world with the same explanation over and over and over, right? Now, but that depends on something being the first time that we resolve, right? And that first time changes depending on when you who resolves it, or which checker gets to resolve it, right? And so there are some ordering concerns that we have to account for. And that means that we can't just, for example, dynamically say, oh, let's see how many CPUs are available. Let's create n checkers and then off to the part. Because then for the next CI build that you do, you get a different machine assigned up in the cloud that has fewer CPUs. And then we do something different. And then all of a sudden you see your errors change. And now, your baseline compares failed and da-da-da-da. And so
that would not be a fun approach to have a different outcome per CPU about.
Exactly. So we gotta like find a way of doing this that is deterministic, or at least deterministic enough that in between different builds, you always get the same result. That is basically that is the one axiom that we have to satisfy, right? And so we're still thinking about that, but I mean, we'll come up with something here. Right now, it's hardwired to 4 checkers, no matter what, which does leave a bit of money on the table. We actually know, you saw in our demos that we compile Visual Studio in, I think it went from 70 seconds to 7 seconds, at least with the current state of VS Code. Or sorry, Visual Studio Code that I'm talking about, right? Now, we know that the check phase, we can make it about even 20% faster than it is right now by running on 8 cores instead of 4.
Interesting, yeah.
But we'll consume some more memory. And is that the right thing to do? Who knows, right? I mean, so we'll see. Because in the grand scheme of things, that means maybe you'll get it done in 6 seconds instead of 7. But heck, you're still like, I mean, whether you're 10x faster or 11 or 12x, is no that last little delta is not quite as impactful, right? So we're working that. That was a long.
I'm interested. That was great. Thank you so much. I mean, yeah, I love that sort of image of basically like multiple checkers sort of stumbling around a file, sort of duplicating work sometimes. And the more people you have stumbling around the file, the more stuff is going to get duplicated, basically. And especially with the global symbol type.
Exactly. Yep.
Yeah. And the so the follow-up I had to that was, is there, you mentioned a couple of times that there's work left on the table, basically, in terms of optimizations in the future that you can see are available. And I think that's pretty obvious because you're doing a port, right? And not a rewrite of the core logic. So there's probably going to be stuff about the data structures and things you can optimize when everything's finished. I'm wondering, though, whether there's any space in the language itself to like optimize in favor of better performance in terms of, let's say, changing the way that global augmentations work, for instance. Or I'm unsure sort of where I might go with that, but yeah, I'm interested in your perspective on that, about how the performance actually leads to different language designs in the future.
Yeah. Well, one of the nice things about moving to native code is that your execution profiles get a lot more deterministic than they are in JavaScript. We have forever sort of battled with this sponginess, I would say, of the platform that we're building on, in the sense that because it's JIT compiled and there's a whole lot of adaptivity that happens in the JIT that we don't get to control. And so we make a bit of a change to our code, and all of a sudden the JIT decides on a different strategy, or it decides to kick out a code page or deopt a function or something. And all of a sudden stuff goes slower, and you go, why did this go slower all of a sudden? I only added code over there, and then it like something happened over here. And there's always this variability that there's this background radiation noise, that you you can't get rid of, right?
Yeah.
Now in native code, it's not like that. It is way more predictable what happens.
Yeah.
And it's actually way easier to profile. And there are some great profiling tools available in Go. We use this tool called pprof, and it'll show you hotspots, and we've used it extensively to optimize our allocation strategies in the compiler already, and it makes it quite easy to reveal places that need further optimization. So we're gonna spend more time on that. I mean, we're already knocking off like the embarrassingly hot spots. We definitely address as we see them, right? But then there's more, that you can downstream kind of go, well, let's go back and look at this again, because there are a lot of allocations here. Maybe we can do better. Maybe we can turn this into inline structures and whatever. One trick we use, and I think has had a dramatically wonderful effect, is pool allocation of data structures. One of the things that's interesting about Go is that everything is just functions and data structures, right? And data structures can be inline allocated. So when you declare a struct, it can either you can dynamically allocate a pointer to the struct, but you can also have an array of the structs where they're just stacked up next to each other. You can stack allocate, et cetera, right? Now, imagine a thing like an AST. In an AST, on average, I think 30% of the nodes, if not 40% of the nodes, are identifier nodes. All identifier nodes, well, they have a string in them, but that's still an indirection, right? But other than that, an identifier node is an identifier node. They're all the same. They're all the same size. Now, originally, we would just allocate them one at a time. So we new up an identifier node. And of course, that leads to an awful lot of small object allocations, right? Which in turn keeps the GC busy, because to the GC, it doesn't matter how big an allocation is. It only matters how many of them there are, because it has to visit all of them, right? And account for all of them. So what we do instead is, instead of allocating one at a time, we allocate arrays, chunks of them, 256 at a time, for example. We actually have an adaptive thing that grows the number it allocates and then ends up at 256. And then it allocates 256 identifiers, and then it chunks out one at a time, as you knew. So it just moves through the array and pieces out one at a time. And so now by doing that, you reduce the number of allocations by 2 orders of magnitudes with some super simple code. And you're not really wasting anything anyway, because these identifiers all sit around forever and they all go away together, right? So we have a pool allocator for each parser that just chunk. And then when all the references to this entire AST is done, then they all go away at the same time, right?
Yeah.
So strategies like that allows us to, I mean, it made things like, if we were to get rid of all our pool allocators, we'd run at half the speed, I think.
Wow.
Of what we do now, or it's dramatic, So
And there's bound to be stuff like that you've missed, right? Like that there must be things that you can optimize in the future.
I'm not sure how much we've missed. I hope we've missed something, because then we can go even faster. But I don't think, I think we picked most of the low-hanging fruit, but there's sort of like medium low-hanging fruit probably that we could still get to. Yes.
Yeah, need to hire some giraffes. Absolutely. All right. So okay, I want to pivot the conversation to talk about the future of TypeScript now and where TypeScript is going, because this is maybe the biggest announcement in the history of TypeScript. And I wonder whether there's another big announcement in the future, or how we imagine the next few years of TypeScript. I'm especially interested in the move towards, and I think this has been in the works for a long time, towards really strong compatibility with ECMAScript, with following the TC39 process really carefully, not adding any new runtime features that aren't in JavaScript and things like that. And a proposal that I've been following quite carefully is the types as comments proposal, which the proposal is that you would bring in some erasable type syntax into JavaScript itself. I'm wondering, because the TypeScript team recently shipped erasable syntax only, which is a flag that only allows erasable syntax, I'd love to get your thoughts on how erasable syntax and the concept of erasability fits into TypeScript going forward.
Well, it's interesting because when you think of, I mean, there's sort of this overarching desire to say, hey, TypeScript can be used wherever JavaScript can be used. That is, I think, sort of the question that the desire that the community expresses, right? It's like, I don't want to have to transpile. I just want to use my TypeScript wherever I would have otherwise used a JavaScript file, and save me that step, right? Now, there are different ways of meeting that challenge or addressing that need. One is to dream up some form of canonically erasable way of expressing your types, such that anyone with little work can do that. And that's what the types as comments or types as whatever, you know, in TC39, you know, like this notion of allowing erasable syntax in JavaScript. Now, the problem there, though, is that you also would want your type syntax to be ergonomic.
Yes.
And nice to read, right? Now, simple erasure schemes sort of often come with these stringent requirements that it be extremely easy to find the beginning and the end of something that is supposed to be erased, right? And that in turn means that you have to have all these delimiters that no one asked for, right?
Yeah. That
aren't there currently because they're not ergonomic. It's not a nice way to have to write your stuff, right? So the community has then instead explored alternative ways of getting there. Interestingly, all along, almost all the bundlers support erasing types, and and through things like isolated modules and isolated declarations, we're making that even more approachable and flexible. And that means, and you know, it is exceedingly rare for someone to develop for the browser and not use a bundler.
Yes.
So that means you have that step anyway. So what's the big deal if it erases the types? What do you know? You're doing it one way or the other, right? So so there's basically no cost there. So there's therefore really no need there either, in a sense, right? And that just leaves Node, where you might run your naked TypeScript files. And now Node has the ability to run TypeScript files through erasable syntax, right? And so, so I feel like we're getting close to satisfying this need through other means. And therefore, there may not be as much demand as there was, you know, originally when this was proposed. And so, but we'll see. You know, we're certainly willing to engage if someone comes up with a brilliant idea where we all go, "Oh, this is fantastic. We should all do this." But but as it sits now, I feel like we actually have pretty good solutions on the major on the major runtimes that where JavaScript runs, right?
Yeah.
And we certainly, I feel like we've engaged as much as we can with all of the players that have interest in this, and that's why we now have, like I said, isolated modules and isolated declarations and erasable syntax only. These are all like, they go in and they just ensure that on our side we do the necessary work to warn you about things that won't work when you go to that other tool.
Yep.
You know, right? So
yeah, you're attempting to hit maximum compatibility, right, with most of the big players, right, in terms of React with
because
JSX.
I mean, we always take this holistic view that we're one cog in the wheel here, right? I mean, and all the cogs have to be there for the wheel to go around. And so we're very eager to work with the other members of the ECMAScript community to make sure that everyone has a happy outcome. Yeah.
Yep. Fascinating. I think one thing I'm interested in the output of, or in the way this is being rolled out, is you've got 6 and 7. 6, which is going to be JavaScript, and 7, which is going to be Go.
Yeah.
I'm wondering if this is like the first ever, like, because you're changing elements of the public API and the compiler and things, is this the first ever kind of like what we would think of as a Semver major change in TypeScript? Like, it probably is, right? An element of a breaking change, because you guys don't follow Semver, and you have
Right.
You sort of have to make your own. Like, I can't imagine what a Semver versioned type checker would look like, right? Because
this is the thing. This is the thing about it. It's like we never think it's okay to break something.
Yeah.
And if you think about it, like, what is our output? What is the type checkers? Well, we have these interesting dilemmas, right? I mean, the output of the type checker, in a sense, at least when you're batch compiling, is error messages, right? And producing more error messages can break your build because you didn't have any before.
Yeah.
Yet when we do our job better, we produce more error messages potentially and break your build. And so, which is it? You know, we can't get better without like causing causing issues, right? So that's why we end up with all these compiler switches, you know, so you can turn off this betterness and say, I'm happy with my good enoughness, you know, but so that's something that we're always having to navigate. But as a rule, though, we backwards compatibility is king in our project, and I think you see that through the 50 whatever many releases, I think, or 40 some releases that we've had so far. It's like you know, some of that code that went through the old type checker, you know, it'll still compile. You know, this is just the only meaningful way of being a type checker. Now that also explains why we chose to port and not start from first principles, right?
Yeah.
Because only by porting are you going to get the same semantics in excruciating detail. You're never going to replicate that if you start from first principles and build a brand new type checker.
Yeah.
So so Semver, no, we haven't. But it's not because we have an issue with Semver, but it's in a sense like, for us, every version should be as backwards compatible as every other version. And just because we've released 10 versions shouldn't mean that, I mean, well, we can call them all 7.124. Whatever. I mean, fine. I mean, but what's the difference? You know, I mean, it's in that sense, then we're still on TypeScript 1. Right? I mean, and in a sense, Go, or you know, Go is like 1.24 point whatever, right? At this point, because they haven't broken anything either, you know.
Yeah.
And
so
that's,
I suppose
that's how responsible players play in this field, right? So compilers are different than frameworks in that sense, right?
Yeah, because I get this question a lot when people ask me about There are a subset of features I think that wouldn't be added to TypeScript now, like enums, let's say, namespaces, things like that. And a lot of people say, why doesn't TypeScript they could just do a breaking change, right? They could just ship, in your words, TypeScript 2. No,
we can't just do a breaking change. No,
no,
because you cause so much pain for so little gain that the equation, it just never works out.
Yeah.
It doesn't, like, and that's just different, you know.
Yeah.
For
Can you just do a little breaking, just like, you know, get rid of strict null checks false or something?
Our little breaking changes are always parked under a flag then, you know.
Yeah.
So you can always opt into the old behavior. And so in a sense, it isn't breaking. The only thing that might be breaking is how we set the defaults, right?
Yeah.
But that's hardly a breaking change. I mean, so you know. Yeah.
Fascinating. So I've seen you answer this question elsewhere, but I will ask it again, which is, you've suddenly got, thanks to this Go port, a massive performance budget, right? Like that you could potentially start eating into a little bit. Let's say adding slightly more complex TypeScript features, adding things that sort of haven't been possible before, but now you've got a bit more room to work with. What's your attitude to that 10x? Like, how keen are you to preserve that 10x improvement, or maybe just sort of eat into it and make it 9x instead?
That very much depends on the particular feature. We are, for example, eating into a little bit of our performance gain because we had to when it came to implementing a canonical ordering of types, which has to do with how we do concurrent type checking and whatever. And we knew that had a cost. I mean, we actually retroactively did the experiment in the old code base, and it was about a 7% cost in the old code base. Now, I don't know that the cost in the new code base, I don't know that we would realize a 7% gain by removing it, but it doesn't matter because we can't remove it because then we can't run concurrently. So that's just sort of like something we had to do, right? So that's a good use, I think, of the newfound performance, because it enables us to actually get even more performance through concurrency, right? What concerns me about the performance gain is because we're Turing complete, it is in the hands of our users to expend the 10x simply by computing types that are 10x more complex, right?
Yeah.
And often these, how can I put it, fanciful libraries out there that perhaps should have stopped a little sooner in their fancifulness, right? But kept on going with template literal types and recursive conditional types and index access types and what have you to, oh my God, look at how we can pick the arguments of the SQL query apart and right?
Yeah, right.
Right. Now, my concern here is that they will simply stop 10 times sooner because it's good enough. And good enough is, it only takes 10 seconds to type check this, right? And so, so it's very easy in a sense, for all of this to just be given up by irresponsible use of Turing completeness, right? So my plea to the community is don't do that. Embrace the performance, write types that are responsible. I mean,
I can tell you've been writing Go for a little while now. It's the,
because otherwise it is way too easy to just give it all away again.
Yeah. I have a couple of friends in the community who are type performance consultants who consult on improving the TypeScript performance, and they're not out of a job yet, it sounds like.
Yeah, no, because it's like I said, it's Turing. I mean, look, you can run Doom in our type checker, right? So it's clearly Turing complete. and look, that took like now what I think Dimitri's going from 1 frame per 10 days to 1 frame a day. I mean,
has he tried it? Oh,
yeah, well, I don't know. I believe he has actually, but but still.
I was chatting about that. Wow. Yeah. Okay, interesting. So we talked a bit about well, features that probably wouldn't be added today in TypeScript. And I'm intrigued by, I mean, TypeScript has been going for a long time. It's, I mean, since you created Steve Luco created the demo?
It's 12 and a half years since we went public. Yeah, October of 2012. I still remember. Yeah.
Incredible. I mean, I mean, incredible reception then too. I mean, what, now that you've come all this way, and now that you have this sort of performance budget that we've now got, what regrets do you have about TypeScript's design? What would you, what did you realize too late? What do you feel you could improve on if you went back in time?
Well, I mean, if it's tough because we know that we have features that if we could, we'd like to shed them and not have them.
Yeah.
Like old style namespaces and or AKA modules, but the old kind of modules, for example, right? We have features like parameter properties, and constructors that, they're handy, but would we go there again today? Probably not. Enums. I personally think they're handy enough that, and I think the TC39 is starting to skew that way, and there's some work to try to incorporate enums, and we will absolutely embrace that if and when it happens. But those are things that, in retrospect, we probably shouldn't have done that. But at the time, it made sense. There was no module system. People had to do something other than just put everything in this big global soup. I mean, that was JavaScript at the time, right? Remember, I mean, we predate a lot of things. I mean, we predate ECMAScript 5 even. Yeah. I mean, it's this stuff goes back a while. And we wouldn't do it that way. We in the original TypeScript, we had a different model for classes because there were no classes. And so it's, and of course we aligned with ES6 once classes started to come into view, but that wasn't until a little bit into the project. So
right. Well, 2015. So imagining a hypothetical future then, where, because I think it's Ron Buckton, right, who is working on the proposal for enums for TC39, or at least the champion. Then imagine then that reaches critical stage 3 of TC39, and TypeScript says, right, we need to integrate this now. With that, I mean, there's a little breaking change in there, isn't there, or a new config flag?
Well, but that this is something that we can address with smart refactorings and compatibility flags and whatever. And we already have similar stuff in place for decorators, like experimental decorators versus ECMAScript decorators, but that's not uncharted territory. We know how to, we know how to fix that.
Okay.
And I think it would be, I think it'd be a boon for the community and everybody to have a sanctioned form of enums, because people do actually want to use enums, and then they have their uses.
Totally.
Yeah.
I think I've seen a proposal knocking around, perhaps on a TypeScript discussion or something, where an erasable form of enums, right? Instead of, you would have an object where you would have the properties laid out, just simple JavaScript object. And then instead of saying as const, you would say as enum or something similar to that effect.
Right. There's been a couple of things. There's one where you say const foo : enum equals open curly, and then you write your enum, and magically you also get some types out of it.
Yeah.
We'll see where we land. I think we want to. I think we want to run with what TC39 is doing first before I would say I would much rather have something that is sanctioned by JavaScript itself, right? Than yet another variation of enums that isn't actually what ultimately is going to happen in the language. It's really only in the case where TC39 says, no, we'll never, ever do enums. Then, okay, fine. but I don't think that we're certainly not there at the moment.
Yeah, I think that's true. So when ES-Build came along, ES-Build had a monumental impact on the way that folks turned their TypeScript files and JavaScript files in bundlers and things like that.
Yeah.
And it was purely because of the massive performance gains there. And it opened up a lot of new workflows and all that stuff. What downstream impact do you think the TypeScript compiler getting 10 times faster, what will that have on the community, on people's developer pipelines, all that?
Well, it'll make the pipelines a lot more efficient, and so we're gonna drink less coffee and and
have less downtime,
to get to wherever it is we're going, right?
Yeah, right.
But beyond that, I've talked about this before also. I don't know, and it's not just markety speak, but I really do think there are some interesting opportunities that are going to open up in integration of type checkers and language services in AI contexts, where all of a sudden we can be a lot more efficient. You see things like the MCP, the protocol, and like where you can surface tools for AI to use, and certainly surfacing something of the equivalent to a language service that can actually validate the code that the model is just chunking out right now, right? Or where the model can ask questions of where is this declared? So I can understand more about it. Well, often that can only be answered by a language service that has semantic understanding of where a symbol comes from, right? So there's some interesting things that are just starting to emerge, where I think being 10 times faster is going to be a huge boon, to making workflows that previously weren't feasible.
Interesting. So do you think that work, because it sounds like what you're talking about is exposing elements of a language server to, let's say an agent is doing a loop, doing some task and letting it call tools, let's say, which access the language server or things like that. So it sounds like you're as a team thinking about adding things to the language server which make that easier and expose that. Is that right?
Well, for example, yes. I mean, but like I said, this is all exploratory, and like these models, like a year ago, they weren't good enough to do any of this stuff anyway, so it didn't matter, right? Yeah. And so this is all emergent. Yeah. But I feel like that we are very well positioned to do some interesting innovation in this space and to sort of cash in on on this 10x gain that we're now realizing, right? In interesting ways.
Well, don't give us too much innovation because we'll all get too excited, and you'll have to go on everyone's live streams every week, and you'll never get off YouTube. You need to do some real work.
I'm doing plenty.
I'm sure.
I was just working our backlog of error baselines this morning. Because now we finally are in a position where we're almost there with the ability to run all of our existing tests from the old compiler. We've been able to run a huge number of them, but not all of the baselines that we produced with the old compiler we can yet analyze, and that's getting close now. So now it's great. Previously we would validate by compiling big projects or whatever, but like this test suite of ours that just touches everything, right? And so it's good to burn that down. And that is also like, once we burn that down, we are going to be 99.999% compatible with the old compiler, right? I mean, down to the exact format of the error messages that come out, right? And so, so it's good stuff.
For those who don't know, I mean, the TypeScript project has an astounding test suite, right? I mean, just in terms of the compatibility, right? Because when I was working on XState core, I remember while we were working on it, it got pulled into the TypeScript test suite, and we were all quite chuffed about that. But you guys compile against dozens and dozens and dozens of libraries, and then the entire of definitely typed as well. Is that correct?
Well, yes, it depends on which part of the dev loop you're looking at here. Certainly, we never merge a PR unless it passes all of our, and I think we are close to 100,000 tests at this point, and they all have to pass before we merge anything. Now, of course, they may change, but then it has to be part of the PR. The change has to be part of the PR, and we are instrumented to capture that, right? That's what I mean by the baselines, which is basically a snap of what was the output, what were the symbols, the types, and the error messages produced by every test that we have in our test suite. That's all captured as a checked-in artifact in our repo, right? Yeah. And then we run the test runner, which produces these artifacts for the new version of the compiler, and then we diff them. And if there are diffs, then you don't get to play unless you analyze all the diffs and accept them, and that's how we get the level of stability that we have, right?
Of course, because it's not just error messages you're producing, right? It's also AST nodes and
it's types in particular. Like, we want to make sure that we produce the same types and that our symbols resolve to the same symbols, right? Because hey, we may not actually have a test that tests this, right, and produces an error if it doesn't. So
ridiculous.
Yeah.
Well, I tell you what, I think thank you so much for coming on. It's been an absolutely incredible joy to talk to you. And we've worked through tons and tons of my questions. I suppose, what's the best way for folks to follow along with the TypeScript project to keep looking and see what's happening with the Go branch?
Well, follow along on our repo, on GitHub. There's an issue tracker, and you can see the PRs that we're doing, and that'll reflect sort of where we're at in the project. If you're a little more daring, clone the repo, install the Go tools, build the compiler, and try it on your code base. With the caveat that if you're using JSX or JSDoc, or you're using project references, whatever, know that that's not complete yet. But a lot of projects don't, and those, I think it's check it out, and if you find stuff, put up an issue, and we're knocking them out as fast as they're arriving. So
nice. Wow. I mean, incredibly exciting times to be a TypeScript developer. Thank you so much to everyone in the chat as well. I think we've had as many as 700 people at once watching this. It's been incredible. So, Anders, I'm going to let you go. I'm going to say a little goodbye to the people on stream first of all, but thank you so much for joining.
Hey, thank you, Matt, and thanks for the great questions. This was a super fun conversation. Yeah, really enjoyed being here.
So I'll pull you off the stream, and then you can just close the tab, and then you're done. Basically, I'll stay on with the crew. Thank you so much, Anders.
See ya.
Bye.
Bye.
Wow, incredible. Oh my gosh. Right. I can't believe that just happened, to be honest. That's sort of how I feel about that. Everyone say goodbye to Anders. This was just a bit of a milestone for me, I have to say, too, actually, to chat to one of my proper heroes. But let's talk about what we just heard. So folks who are following along, send me your questions. What do you think? I'm just going to open the window. Be 2 seconds. More streams? Yeah, I think I will do streams. Great questions asked and not asked. Yeah, I was super keen not to do the Rust stuff. Big in. Yeah, it was big, Gabrielle. It really was big. Ashley, hi. Thank you, Mr. Anders. Yeah, I mean, the guy can... The thing I really like about him and his style is that he's not only... And this is true, actually, for all great developers that I know. They're not only incredible writers of code, they're also incredible communicators. I mean, and just the way he's able to explain things is just wonderful, because I don't know, it's brilliant. This World Books in the background, Catan, This is actually my rejects board game shelf. I've got a bigger board game shelf downstairs. I am proud, Aaron. I really am. That was wonderful. Answered a lot of the technical questions. Got you covered. Cool. Yeah, I'm glad, Tris, that that you felt that way. I really didn't want to go in nuts. Yeah, Trash. Even you can understand. Oh, blimey. Yeah, I mean, everyone's asking why not Rust. I think they did such a good job explaining why not Rust. Like, it's just obvious when you see the code side by side, like they did in the presentation. It's just obvious how that it's going to be way more navigable for contributors. If they considered building a native TS compiler instead, I mean, that's been sort of done before, right? I think NativeScript did something like that. That just seems like too big a lift, right? Compile the existing TS compiler to native. There's like multiple steps there. I found it really fascinating what he was saying about never ship a breaking change. Never, ever, ever ship a breaking change. Like, there are, like, when you're operating at the compiler level, you just don't have the flexibility that you have when you're a library or a framework. You know, and that's their philosophy. We try Go in the future.